Hello, everyone. We're the team Yelp Helper, and for our capstone project, we've built a recommendation system using Yelp data. And here are the five of us. For the audience here, we would just skip the introduction for ourselves. The outline of the talk is pretty wordy, but very quickly we'll talk about the background of the project. We would show a few EDA slides and talk about the data storage and access. And then we would zoom into first the recommendation algorithms. We actually implemented 4 different approaches. Then we would move to the engineering part, talk about the data pipeline, the app itself. Hopefully near the end we can give you a live demo. The motivation really, very briefly, we want to work on something with real business need. We want to practice dealing with big data, at least gigabyte size level, and also we want to practice the machine learning algorithms we've been learning in this class. So we chose this Yelp Helper project. It nicely sits at the intersection of our goals. And our project architecture looks like this. On the front end, it's a Flask app. That's the web page. Near the end, we're going to demo. And the back end is a machine learning computational box sit in the cloud using the Databricks engine, which is basically using Spark and Amazon cluster farms. On the outside, we do have we do use the Amazon RDS and also the S3 for structured and unstructured data. And for the communication between the front end and back end, we use Kafka and we do structured streaming. If you zoom in a little bit, we're first going to talk about introduce the data. We're going to talk about our external database. Then we're going to zoom into this computational box to talk about each of the 4 approaches. Then we're going to switch gear to talk about the engineering part, then the demo.
Okay, so I'm assuming everybody knows what Yelp is. It's the website we can go on to before you go to a business or to a venue. You can see what it's like. And you could also go on Yelp to, after you're done going to that business or venue, give your review. So it was definitely a good choice on our part because it allowed a sense of like hardly 5 gigs is big data. It sort of was like close enough so that we could use sort of big data methodologies like Spark and like MySQL, even though you don't need big data for MySQL. But yeah, essentially there's a lot of data that is available on Yelp from actual users that are collaborating with Yelp, but also data based on the business, based on like the location, the attributes, the tips that people give. Why does Yelp do this? Yelp basically does this. This is the 9th round of this data set challenge. I think it goes back 4 or 5 years. And essentially, Yelp has a really good data team. You go on, they have all this data available from even photos that they categorize so that you can get a better understanding of what the business is like or the restaurant is like before you go. They let out 5 gigs of data from reviews, tips, users, businesses, photos, so that they could see what you do. They want you to go in and build a better recommendation system than they have, or they want you to impress them with any sort of project that they haven't come up with already. And so that's sort of why we took on the challenge. We wanted to see whether or not we could do something that Yelp hasn't done. And it sort of we had a huge range of different sorts of data to work with. So similar to Jack and Hen, we used Amazon's relational database service. In this case, we implemented MySQL, and 5 gigs, again, not that much data, but some of the data sets that were included, reviews specifically, were 4 million rows. So you can't really work with that a lot of the times in a CSV file, or you can, it just takes kind of a long time. So if you upload it into MySQL, it makes it pretty easy to query the specific data that you want based on location, based on maybe specific user. There were tips. Tips is like, vegans love this place or something like that. That is just a quick snippet of an overall view of what a restaurant is like. I probably should have mentioned, we only looked at restaurants for our specific set. I mean, there's a lot of different reviews for venues out there, but restaurants seem like a good way to narrow it down. Businesses, again, the attributes, there were over 44,000 businesses included in this data. Check-ins is just when people actually went, and users. Specifically, what we were interested in with users was their social network. Social network, we could see how many friends a user might have, how many reviews, how active they were on Yelp, and we'll get into that a little bit later. So this is the schema visualization. A schema is sort of like a floor plan to a house. It basically shows the structure of how the database and the tables are laid out. So we have 5 main tables, one being for the business. The business ID is included in that. The check-ins, the number of reviews, the overall rating. The users is another table that we did. This is the average stars that a user would give. How many people thought that how many people thought that that person's reviews were cool or funny. Reviews, again, is the biggest table that we had. How useful it was, how many stars they gave it. Check-ins, which we didn't really touch too much, and tips. So we had a bunch of data. We sort of wanted to take a look at some of the reviews first so we could apply some NLP. And so this is an EDA of basically, it's similar to a word cloud, except it combines. On the x-axis is basically showing the good reviews frequency, or how frequent a word was used in good reviews, and then the y-axis is how often a word was used in bad reviews. So this is sort of a small sample of every review that we have, but it's kind of cool. You can see in the top left, tasteless, charged, gross, rude, obviously all words with negative sentiment that you would expect are associated with bad reviews. And then on the bottom right are mostly words that are used with good reviews and not with bad reviews. So I highly recommend Grub, Filet, great experience, Sliders, karaoke. People love karaoke. And then the top right are sort of words that are more general, that aren't really descriptive towards anything. It's just food, good, ordered, waitress, manager. And then the color is sort of giving you a gauge of what these words, where they fall. So red and darker colors more fall towards the good reviews, and then the lighter colors are more towards the bad reviews. On the right over there, you can see what are the top bad words and top good words, and then the characteristics are just words that were sort of used for both. That were these words were seen. They're not n-grams, they're just unigrams, but they were seen in both bad and good reviews a lot of the times. And then that will lead us to what we did with the reviews and the sentiment analysis with Sean.
So we wanted to use natural language processing for our actual recommendation and go past EDA with that. And so the first thing we did was some sentiment analysis. And so the sentiment analysis workflow is pretty basic. You start with the pre-processing, go to the neural network, and then actually get the sentiment out of that. So for pre-processing, you first have to encode everything in Unicode, and then you binarize it. That means that we took the reviews that were rated 1 or 2 and put them at a 0. We took the reviews that were rated with 5 stars and put them at a 1. We then tokenized the words and then used Keras' packages to do text to sequences, which just means that we took the review and listed out the indexes in a vocabulary dictionary, and then padded it on the end with 0, so all the reviews were the same length. We then put it into a neural network. This neural network was supervised because, like I said, we binarized it in the beginning. We gave it ratings of 0 or 1 and then performed from there. Then there was some convolution and pooling involved, and then we got our results. It was 94% accurate for the train test split. And then we just spot checked it by writing our own personal reviews in to see if it actually caught our sentiment in our own reviews. And it was pretty good at that too, unless you gave something that was self-contradictory, kind of like the phrase "nothing special." It's kind of hard to pick out whether that's positive or negative. And then we used those sentiments. We applied it to all the reviews across the board. We averaged them out by business and then gave that as a feature in our base recommendation. And then convolution and pooling, this is just what that looks like. So convolution is when you take a filter and you slide it through your data, pulling out some aggregate information. Pooling is where you go at the end and you take the most important features, they say. So you would take the max feature, which would be the dark red, and you put that into the next layer. So aside from just gaining features that we can use in another recommendation, we also wanted to do some content-based recommendation. Content-based recommendation is just item-to-item recommendation based on the user profile. So on Amazon, if you buy a book that's of a certain topic and you like that book, you rate it really highly, it's going to suggest other books that are a similar topic to you. And so we wanted to use this by implementing a keyword search onto our app. And then based off that keyword search, we would then use an average word-to-vec model to recommend similar restaurants to what you wanted to search for. So cosine similarity and word-to-vec, the workflow is pretty similar to sentiment analysis. You do pre-processing, the neural network, and then you get the results, the similarity in this case. For the pre-processing, you tokenize and you take out stop words. This neural network, however, is unsupervised. We don't really know what we're looking for at the end. And so it just like goes through many iterations until it figures out something that seems reasonable, finding the patterns in the words themselves. We use Spark's MLlib, which uses a skipgram model, and some of the hyperparameters, for instance, were just that we wanted a vector size for each word of 100 features. And then in the end, you should be able to get these words into a feature space, and similar words point in similar directions, which means that you can run cosine similarity to see how similar the words are. And then we would provide a rank. And so, for instance, the word Chinese, when you search for it, it's similar to Asian, Cantonese, Filipino, Shanghainese, and Korean, which seems to be pretty accurate. The more data you put into this, the better it is. Yeah. And this is kind of what it looks like in like a two-dimensional space. Words that are similar are nearer to each other. King and queen are higher up because they're with royalty. King and man are over to the side because they're both like same gender. And then now that you know their vector space, you can actually perform algebra on them, which is pretty cool. So if you look back before, man is this large and pointing in that direction. If you take man away from king, you're going to start at the king space, take away man, add in woman, and you're with queen. And so here's a little test for you guys. If you start with filet mignon, you take away the aspect that it's beef, you add in seafood, what could you maybe get? You guys are right, lobster tail, which is pretty cool. And so you guys just saw the first one, you get lobster tail for that. What about a fork that you use for soup? Or a drink that has barley in it? You get spoon and beer, which is pretty cool that it recognizes those patterns and those relationships between words. And so just to sum up the NLP, we use sentiment analysis to rank all the reviews and then put it in our base recommendation as a feature. And then we use word-to-vec to find cosine similarity between reviews and then use that for content recommendation.
Sean just talked about one of the four branches in our recommendation engine, which is the NLP. And I'm going to, for the next 4 slides, we're going to talk about 2 other approaches we implemented. One is collaborative filtering. Another is a social network deep dive. So what is collaborative filtering? Imagine you have a group of users. Each of them have some rating on these items. And if you put the users and ratings, users and items into a matrix like that, you have this rating matrix. And when you try, for example, you see a question mark here. If you want to predict the rating from this last user on this item, you want to predict that. Basically, what collaborative filtering does is it tries to find similar users who gave similar ratings on items you've rated on, and then try to predict your rating, assuming since the 3 of you voted similarly in the past, for this item you might vote similarly like them. And this is actually a good example of a user item matrix. In reality, of course, for a system like Yelp, you have many more rows because you have many more users and also many more columns. And in reality, it's usually very sparse. And to take advantage of the sparsity, people use this matrix factorization, which is trying to use a smaller matrix U multiplied by a smaller matrix P to get an estimate of this complete user item sparse matrix. And the model train process is basically trying to minimize this cost function. And this first term is the error estimate, and later you have some kind of a penalty or a regularization term. We used the matrix factorization library included in the MLib package, which is Spark friendly. So that is collaborative filtering. And this is something else we were very happy to implement. So in this database, all the source files are JSON files, so unstructured files. And for each user, that user is a dictionary. Within that dictionary, you have these features describing that user. And for the friends feature, it's actually an array of encrypted IDs. And we tried to take this unstructured data out and build this for whoever is a little familiar with how to construct these social graphs. That's the edges. So in these pictures, each node is a user, and then to describe the connection between these two users, that's an edge. And the information you need, basically this user ID and that user ID. So for this row, that's describing the connection between these two users. So after you convert the unstructured social network to a structured, it gives you the ability to quickly search in the user database and search through their social network. Then the idea that we implemented, the most fundamental idea. Basically, this is you, and hopefully all 5 of us are your friends, and you are somewhere at the middle of the map, and you want recommendation. Instead of trying to ask the system to come up with a similarity calculation or collaborative filtering by assuming you are similar to everyone else, we just dive into your social network, assuming you like what your friends like, or hey, you dislike what your friends like. We'll let you know what your friend said. So assuming on the restaurant number 1, Reza gave it 5 stars, Andrew gave it 4 stars, so we would tell you that's a 4.5-star restaurant based on your close friends. And if Sam gave the restaurant number 7 a 4-star, but Sean gave it 2-star, we would tell you on average it's a 3-star based on your friend's opinion. That was that third approach. Then we would move on to another, which is the 4th approach.
Okay, so everything so far has been assuming that the user is providing some additional information, but most of the time users just want to get quick results based on their location. So this is going into the base level, almost instant recommendations that we provide. So in the data set, we have reviews that are almost 14 years old. So our question was, how relevant are these reviews, and should we take them into account at all? So we passed all of the reviews through this filter, essentially de-weighting 40% of them by some amount, meaning that the newest 60% of reviews are fully accounted for. On the business level, we had a few different approaches. We noticed that the check-ins and the reviews were both significantly skewed. So we applied log transformations, and we weighted the check-in count a little more because we thought that was a better indication of popularity than reviews themselves. Using Sean's NLP sentiment score for each business, we multiplied some amount to the time-weighted reviews, so on the review level, and then we averaged that for each business and plugged it into this final score formula. So it's a combination of sentiment, time weighting, and also popularity. And on the bottom here, we see our final distribution. So it is somewhat skewed. You can't think of it in the sense of a uniform distribution. For us, 4 stars is amazing, the top 40 in Vegas, all the way down to 1.5 stars, which basically means it's complete garbage. And then just for note on the right, I have a plot showing the sentiment, this final rating distribution, and average base stars, which is what Yelp provides. And you see a strong correlation between the sentiment and the average base stars, which makes a lot of sense because if a place has only a few reviews and say it's really good, really positive, it's going to show up really high on both sentiment and average base score. For us, however, if we're taking into account the popularity and we take into account these other factors like the time of the review, you're going to lose that correlation. And essentially, we're saying that our measure is a little bit better than what Yelp currently provides. Putting it all together, we built a flexible system that can take in required a location, so where you are, and we'll definitely give you some results. The user ID to do social and collaborative modeling, and also keyword to do NLP-based modeling. And as a result, we can dynamically generate up to 40 recommendations within 20 seconds.
So now we've seen all these different models, and to get these models across to a user, we built a Flask app. So this is our front end. On the right side, you see the different categories where you can, is it better now? Where you can input the different parameters that Sam just mentioned. And we'll go more into it when we do the live demo. Chao mentioned earlier that we use Kafka to communicate, and to communicate our front end with our back end. And I'm just going to quickly go over what Kafka is to kind of give you an overview before I go into how we implemented it. So Kafka is a stream processor, which allows you to stream information from one end to another end. And it's got 4 major components: brokers, topics, producers, consumers. Brokers are... Is there feedback? Okay. Oh, I'll stand here. So brokers are the servers which the information is being sent through. So if you have a lot of information and one server can't handle it, you can have multiple brokers set up. Topics are, you can think of as channels and where the information is being sent through. So if you need one topic for information going out and one topic for information going in, you can set up topics in that manner. And producers and consumers are when messages are produced and when messages are consumed. So on the next slide, when a user makes a request on Flask, it produces a message through this first topic, and then on Spark's end, it consumes that message. And then vice versa, once Spark has processed, gone through our models, it'll produce some information, and then on the Flask end, it'll consume that information. So Kafka is kind of a new technology, and to get it to be used more effectively, Spark has recently introduced this thing called structured streaming, which is an alpha stage. And what it allows is that when you have data coming in, you can imagine that data being streamed in is just as reading or querying data from a bounded static table. And in this way that you see that it's an unbounded table, every stream that comes in is like an appended row on your table. And what makes that really useful for us is that the type of syntax you use when you're coding or when you're calling things from a table or from a stream is the same, but you just add read stream or write stream instead of read or write in Spark. Okay, and yeah, what's the time count? So here is a quick video showing the different components of our screen. So on the top right, we have, I just created a Python script to go through every observation. So every 2 seconds, it'll send a row from this observation into Kafka. This is just a representation of Kafka taking in every stream. This is how Spark reads it in. And on the top left, I have a producer where you can manually enter in data. And you can see on the bottom, Spark will also read that data. So this is all in boring command line interface. So we're going to show you a live demo of our app. AW. Okay. So to start out, I'm just going to do no keyword. So as Sam mentioned, there are different ways to approach this. If you put in just your location, it'll just give you a recommendation based on that. If you put in a keyword, it'll also take that into account. And if you put your user ID in, it'll also take that into account. For our project, we focus mostly on Vegas as the first place to test on. So that's why it's right now centered around Vegas. And depending on how many parameters you put in, the search takes a little bit longer. So when we do our base case, where it's just looking at where you are and not putting a keyword in, it'll be a little bit quicker. So here, it gives you the blue, which is just the location-based responses. And now if I add a keyword, it'll take a little bit longer because now it's going through also the NLP models. And the purple represent the NLP responses. So Roberto's Taco Shop, Mexicana, Restaurant El Rey, tacos. And then if we enter a user ID in, it'll pop out with red pizza slices once it's gone through the matrix factorization modeling. And also the collaborative filtering. So the collaborative filtering is social. And we'll share the link with you all after our presentation so you can play around with it too if you'd like. So here we have both green slices and red slices representing your friends using social, and also green using collaborative filtering. Any questions?
Just very quickly, we gained experience we wanted. We play with recommendation and implemented recommendation algorithms. A few of the algorithms we came up with ourselves, and we dealt with big data. For all of us, we've been almost working in Databricks cloud-based environment entirely, and the five of us, we were kind of working as a little startup. It's pretty fun. And for future work, I mean, there are definitely things we want to keep polishing on the front end, and for back end, we feel it's really just the start of the fun part. Now the 4 different approaches are working. I mean, there are tons of things we can do, as all of you guys can imagine. And we want to thank a few of our instructors and all others who helped us. And this project was also inspired by some of our previous cohort students' capstone project. We really like how we arrive at the live demo before this weekend, so we actually had some time to have a little fun. But really, he's doing work. So. Thank you.